So we've seen that if r equals constant, if the magnitude of our r vector is constant, means we're moving on a circle, and if if the magnitude of our r vector is constant, then its derivative is simply a multiple of u theta, which means that its velocity is in the direction perpendicular to the radial direction. The radial direction being perpendicular to the circle means that r prime is perpendicular to the circular path. The second derivative consists of a multiple of u theta, a component of acceleration in the direction of the path. I keep moving my minus sign here. And u sub r, a component in the direction toward the center. Now that's because we have a negative. This is toward the center, provided r is positive, which it is since it's a magnitude of a vector, and theta prime squared is positive, which shows that this component of the vector is always pointing back toward the center. Now, looking at a typical r prime vector, it has a component in the direction of the u sub r vector. That component has magnitude r theta prime, excuse me, opposite the direction of the u r vector, and component r theta double prime in the direction of the motion perpendicular to the radial direction, so that we see that this vector is indeed negative r theta prime u sub r, and this one is r theta double prime u sub theta. And we want to look at the meanings of these two components. So r theta double prime is clearly then the acceleration component in the direction of motion. A couple of notes. If theta prime equals constant, then again, if we interpret this in terms of motion with t representing time, then theta prime, r theta double prime, is the velocity, which is constant. And actually I could have said that this condition holds if and only if this condition holds. These are equivalent conditions. If the velocity is constant, then the particle isn't, if the magnitude of the velocity is constant. I guess I should do this. Okay, so if the magnitude of the velocity is constant, then the object isn't speeding up or slowing down. And that's consistent with the idea that if theta prime is constant, theta double prime is 0, so there's no acceleration parallel to the direction of motion. Now, we can work backwards. If theta double prime is not 0, then r theta prime cannot be constant, because in order to get a second derivative not equal to 0, well, if theta prime isn't if theta prime is constant, theta double prime is going to be 0. So if theta double prime isn't 0, theta prime is not constant, and this isn't going to hold. And if theta prime isn't constant, then we do have acceleration parallel to the direction of motion. In other words, the particle would be speeding up or slowing down. Now, r theta prime is your acceleration component perpendicular to motion, this one. And of course it's toward the center, because it's in the negative direction, in the direction opposite u sub r. And we can look at this in a couple of ways. Okay, r theta prime And you know I've got a mistake that I've been carrying through here throughout, and I'm going to have to go back and correct that. That's r theta prime squared. It's a good thing because I was going to get stuck right here if it was just theta prime. Okay, so that's r theta prime squared. This is r times theta prime squared, and this is r times theta prime squared. Have an extraneous set of parentheses here. In any case, r theta prime squared is what? That's r theta prime times theta prime. Why do I write it this way? Because r theta prime, in the interpretation where t is time, is just the velocity. And of course theta prime is still theta prime, but since r theta prime is the velocity, theta prime is the velocity over r, so that r theta prime squared equals velocity times theta prime is v over r, and we get v squared over r. Acceleration component r theta prime squared then implies that we have an acceleration component v squared over r, v squared, I wrote v squared over 2, that should be v squared over r, and I'm going to kind of obliterate that, and we're going to say that's v squared over r. Okay, so v squared over r is our acceleration component back toward the origin, and that's something at least familiar to physics students. That's your centripetal acceleration. So from this picture, from the radial components and the derivative of the velocity vector in the radial system, we conclude that motion around a circle consists of or implies that at every point you have an acceleration back toward the center, which we call its centripetal acceleration, which is v squared over r, or if we prefer, r theta prime squared, and a component in the direction of motion, which is just r theta double prime. And it follows then that our acceleration vector, which we've seen to be equal to this expression, expresses our centripetal acceleration equivalent to v squared over r, and what we will call a tangential acceleration, and acceleration in the direction of motion. Of course, the acceleration will be in the direction of motion if theta double prime is positive, and opposite the direction of motion if theta double prime is negative.